As usual, we're going to get questions. We'll do on that side of the room. Get close to Ryan and he'll let you ask the questions. I think I'm going to start with a quick one, although it's a bit of an elephant in the room. You also mentioned that, you got asked to change AI, in both of your works. I would say you are doing probabilistic machine learning, the conference called Machine Learning for Healthcare. Thoughts on when to approach problems in healthcare with a probabilistic machine learning approach versus maybe more advanced AI, LLM tools? Is it a problem-dependent issue? Shall we just move on and call everything AI and is our life easier that way? I don't know, just to start a conversation going. What are your thoughts?
Okay, first, I'm not sure if I would call the LLM models more advanced, but I think there are multiple dimensions. So I think you should always use the model that is best suited for your problem, right? And as you saw, many of my projects are in pediatrics, where data size is small, and just train a model from scratch would not be possible. So we often have very tiny data sets, so then just training would not, so this was just not feasible. And also what I mentioned is that often my collaborators would like to have some notion of interpretability, and also, yeah, this is then for sure not given. But yeah, I give over to you and then
yeah, I mean, I would agree. I think it's getting more and more blurred. I think of the machine learning as more kind of like engineering solutions. So this is very much we wanted to engineer. And for us, we wanted to use simple models because we wanted to understand, we wanted to get interpretable results and build up the complexity, I would say, but starting from the simplest possible models that we could fit. And so the other thing which is really important is application driven. So there are many, we've heard amazing talks using large language models and neural transformer architectures, and they're really warranted, but it's kind of application driven.
Okay, thanks for your thoughts on that. I guess we'll open the floor with the first question.
Thank you, both of you. Beautiful talks. I have a question actually for Dr. Julia Vogt. I really like the echocardiogram. That was for pediatric echocardiograms, right? So I just had a question. When you're dealing with ultrasounds, there's a lot of reflection, refraction, aliasing, and artifacts that can be captured in the images. So did you have like a pre-filtering stage where you removed images that had these things, or did you classify these as like, was there ever like, how you have the concepts? Was there like concepts for like, these are things to avoid, or like these are like, gonna corrupt the interpretation?
So for the ultrasound images of the heart, so the heart is a very defined region, right? So what we always did is we cropped it in the size of the heart so that it's always the same size, and we did some pre-processing, like also augmentations and adding noise and so on, that we take care of artifacts. And then these concepts are predefined, and they will always be in this region. But what we realized is that often the model, so the first versions of the model, found some potential defects actually at the boundary of this cone, right? So then in the next versions we made sure that we define a model that is circular and just defines this inner region to make sure, because we know at the boundary of the cone there will be no artifacts, but this is where the color changes somehow, right? And this was somehow captured. But yes, and so far we only did this in one hospital, so we have only one type of ultrasound machine, right? So I think if we change the ultrasound machine, we again need to make sure that we pre-process this in a right way to make sure we're not having some weird artifacts that we take into account.
Thank you.
Thank you.
I have a question for Professor Holmes. I really like the model you built. So my paper is very similar to yours. And my question is, how easy it is for, how is it very tough to use the model you built for other diseases? Because it seems the model you built is very specific to MS. If other researchers or clinicians want to use the model for other diseases, how difficult it is?
Well, at one level, it's very general. So, as in probabilistic factor analysis models driven through hidden Markov models. That's a general technique. So I think what we did is kind of piece it together. So we did the sparse factor analysis because we knew that a lot of the kind of multivariate measurements were highly correlated. And so you need to be careful if you get very highly correlated variables that they don't kind of dominate. So you imagine you could have 1,000 highly correlated variables, yeah, and then like 2 uncorrelated ones which are really important, and then the 1,000 correlated ones can kind of dominate. But if you put a factor analysis model, it can kind of pick that out. But the use of a kind of a factor analysis as a kind of generative model off the back of an HMM, of a hidden Markov model, that's a pretty broad class of models. So, I mean, whilst you wouldn't use the load-ins and the weights from what we've done, the general approach could be applied for disease progression or patient trajectory model.
Okay, thank you. Another question is, so I saw you only have eight biomarkers, but what if a disease have, as you said, 1,000 biomarkers? Is the model still applicable here or not?
Yeah, it is. You'd need enough data to be able to kind of identify, but the kind of sparse factor analysis model is pretty scalable. So I wouldn't be worried if you had 1,000 measurements.
But what about the runtime? So is the computational cost?
It would depend on what compute you've got, how much data you've got. Yeah.
Thank you.
It's pretty quick though.
Hi. I also have a question for Dr. Holmes. So if I understand your model correctly, you're kind of basing it on the assumption that you have these different stages of progression of the disease, that basically everyone has a certain probability of transitioning into. Have you looked into kind of breaking that assumption and saying, okay, I'm going to try to distinguish different maybe subtypes, either by patient or by disease subtype, that will tell you or allow you to predict either the full kind of path or at least differential, like different probabilities of transition, depending on, you know, things that you may know from the beginning of the disease progression.
Yeah. So I think the question is that the way the hidden Markov model is that if you're in state, say 3, say this table is in state 3, you all have kind of equal probability of jumping into this table, or you all have. So what you can do is you can try and condition and do conditional state transitions, which says, well, if you're all sitting around table 3, but I know something about you, then maybe I alter your transition states. So then on those arrows, then they become conditional probabilities of moving. It's a really interesting idea. We didn't do that.
Thank you so much to both speakers. My question is for Dr. Holmes. So I was wondering, how were you able to sort of like determine that optimal state space dimensionality and deal with the model selection? And then the second one is, what are some of the advantages of using Bayesian statistics, Bayesian optimization, and hidden Markov models as compared to just, you know, taking all the brain images and fitting that into a large language model?
Yeah. The first question was, how do we choose the dimensionality of the number of states? So the 8 states in the hidden Markov model we chose using something called the Bayesian information criteria. The Bayesian information criteria looks at the likelihood of the data. So there's a fidelity to the data. How well do you kind of predict the data? But then what we know is you can't just use that on its own, because the more complex models, you add you can keep adding parameters in, keep adding states. Of course, you're going to do a better prediction on the data that you've got. So it has a penalty in there, the BIC. So then you have this kind of regularization. So you've got a fit to the data plus a penalty on the number of parameters, which is also a function of it's like P log n. So it's like you penalize the number of parameters times the logarithm of the number of data points. And then we fit models of different dimensionality. So we fit the model with like 4 states, 5 states, 6 states. We went up to like 10 states, and what happens is you get this sharp elbow where it drops, the loss function drops to when we've got 8 states, and then it goes a bit flat. And what happens is when you go to 9 states, 10 states, you take one of those tables and you break it in two. So you take a state and you subdivide it, but there wasn't enough evidence to really suggest. So it was a bit heuristic, but when we looked at that loss function curve, we said, we'll go for 8. And I've forgotten the second part of the question. But
The second question was the advantages of Bayesian optimization and hidden Markov models over training just a large language model and feeding then all the brain images.
So this is an underlying generative model. So we wanted to do a joint probability on observables. And I think if you want to build a joint probabilistic model on observables, there are very strong reasons why Bayesian is an advantage. That said, we had to do a lot of computational shortcuts. So we did things people might know, Laplace approximations. We used a lot of kind of EM algorithms, expectation maximization algorithms in there. So it's not kind of fully Bayesian, but we tried to adhere to the kind of joint probability models of Bayesian inference.
My question is also for Chris Holmes. I'm really impressed by how your work is kind of a success story for the classical probabilistic machine learning paradigm in a very useful setting. I think I'm very influenced by the spirit of the age, but upon seeing a problem like that, my first instinct would have been to say, oh, MRI, I need a deep neural network somewhere. I could make it Bayesian somehow, but in the features, but I put deep neural network there. I wouldn't do a factor analysis because would I be so lucky that things would be linear? I'd throw a deep neural network in there too, and then I'd kind of throw everything I had at it, try to maximize like quote unquote accuracy, and then try to do interpretability post hoc. So I'm really impressed that you stuck to keeping things simple and you got a fantastic result. Do you have comments on, do you think that approach works more than we think it might, and that we might be too quick to reach for deep neural networks in settings where we want to understand what's happening?
Well, first caveat, we started this work probably 5 years ago. And what would happen if we started today? I think we would still do this as a baseline. Yeah, because I think if you dive in with, say, deep generative models, you wouldn't have picked out that there's actually quite a simple kind of latent structure. Now, whether we can improve the resolution and the interpretation of this using more modern deep learning methods, that's to be seen. We're currently building diffusion models on the brain imaging, which would allow us to, rather than take summary statistics that we model through the latent factors, actually build deep generative models. Whether we would get them to scale around 200,000, we've got 200,000 brain images on 35,000 patients. That would be a considerable kind of computational resource that you would need to put together on that. That said, I think it would be really interesting to try that stuff.
Thank you for the fantastic talk. I have one question for each of you. So first, Professor Vogt, I'm super interested in the interpretability of deep learning models. But as you said, the explainability post hoc is usually not unreliable, and the intrinsically interpretable AI model are like super difficult, and they are black box like in nature. And I hear that some people think the inherent interpretability is the way to go for high stake decision making. There are also other people saying the performance kind of origins from the black box nature, and they argue that we still don't fully understand how Talanoid works. Maybe as long as we use rigorous trials and make sure the performance is good enough, we don't need to bother with the mechanistic interpretability. I'm wondering your perspective on whether intrinsic interpretability is the way to go.
But I would not say it should be either interpretable or explainable. It really always depends on the problem you look at. So, and you should, I think, always take the easiest model possible and not take complex models if an easier model works. So we have seen here that if you have a model that is sparse, and sparsity is one of the most intrinsic interpretable models that you see exactly which features are picked. If that works, it's great. But if you really need the black box because the classical models are not powerful enough and you need really the large deep neural networks, then you need to go for the post-hoc explanation if you really need the explanation. I mean, not always explanations are, in not all applications, explanations are needed or necessary, but if you really need them, I would say, I would not limit myself first on which model to choose, but say which model is the best for my application. And if it's an interpretable one, great, but if you really need, for some reasons, to have the larger models that are more complex, where you just really don't know what's going on, and you need an explainability component, then you try to later on see what is happening there. So I would not say one is better than the other. It's really application dependent.
Thank you. The second question is for Professor Holmes. I'm really impressed by your model, and I'm just wondering, in your external validation, why still fitting the model first, but not just take the outside data and classify them into your identified states using your development cohort and see whether the probability trajectory or transition probability changes.
Yeah. So the first part to that question was, and in the title of the talk is around, and in the paper is around reclassification. So what we see is one of the big kind of take-home messages, or one of the big insights that we've got, is that we think we could argue that people should be thinking about these 4 states in particular. Well, eight underlying states we see, but we can cluster them into 4. And so that was the primary thing that we wanted to replicate. What's the evidence for the 4 states? So when we went over to Roche and we got the data, we were interested to kind of run in the model, run in the things like our characterization of the states, and seeing if it matched onto the ones that we found within the Novartis data, and it did. So we could have just taken the model structure and looked at the different trajectories. So the actual the transition probabilities were different, but you would expect that because you have a different population, because there were different clinical trials. So I think one of the states, one of the 3 original kind of conventional classes was missing in the Roche data. So we were expecting that the transition probabilities would be different between states. But we were hoping, and fortunately it did, is that the overall structure of the of the latent states replicated, which it did.
Thank you very much.
Yeah, thank you both for the great talks. My question is for Dr. Vogt. My first part of the question was just asked. I was curious about your general ideas about interpretable, explainable, but instead I'll ask maybe a little more detailed question. I thought that on the echocardiogram project, the way that you use the reconstruction of the healthy heart in comparison to the actual image was really lovely and an intuitive way to see where the differences are. A lot of the time people might just have settled for a post hoc explanation like GradCam or something like that, which would probably be a lot fuzzier and harder to interpret. I'm just curious if, behind the scenes, if you contemplated using one or the other, if there was any interplay between maybe what the clinician thought was more attractive.
So there was a lot of back and forth with the clinicians, what is actually usable for them, and we tried many different models, and in the end we used the one that, in our feedback loops, they said is actually usable and feasible for them. Because what we want to do is we want to, in the end, bring this into the ultrasound machine so that in real time they see this, and this also needs to be something that is, like, for them intuitive and also somehow feasible to put into these machines. And this is also where we need to now to talk to the ultrasound provider, what can be done and what is feasible. And this is a complete different area, but yeah. So this post-hoc explanation was something that they really wanted to have. And I mean, which model in the end for the clinician, it was really just what is visibly the easiest for them to see and how can we show where it is, but which model they didn't really care too much.
It seems there are no more questions and we are almost at 3:30, so I guess we'll leave it here. Thanks
Thank
a lot
you.
for the talk.
Thank you.